Good morning everyone. My name is Anna Neural. Today I'll be presenting on return-oriented programming, or ROP, a sophisticated exploitation technique that has fundamentally changed how we approach software security. This technique represents a critical evolution in the ongoing arms race between attackers and defenders in cybersecurity. So, what exactly is return-oriented programming? ROP is an advanced exploitation technique, some call it an art form, that allows attackers to execute malicious payloads without injecting any new code into a program. Let me emphasize that, no new code injection required. Instead, ROP works by reusing existing code snippets that are already present in the program's memory. We call these code snippets gadgets. Think of it like a literary remix. You're not writing new sentences, you're carefully selecting and rearranging existing sentences from books already on the shelf to tell your own story. This technique is particularly powerful because it bypasses many modern security mechanisms that were specifically designed to prevent traditional code injection attacks. To understand why ROP is significant, let's look at how traditional software exploitation used to work. In the past, exploitation was relatively straightforward. An attacker would find a vulnerability like a buffer overflow, inject their own malicious code, typically called shellcode, directly into memory, and then redirect program execution to that shellcode. The process looked something like this: overflow a buffer, overwrite the return address to point to your shellcode on the stack, and when the function returns, your code executes. Simple, effective, and for many years, this was the standard approach. But the security community didn't sit idle. Several powerful memory protection mechanisms were developed to stop these attacks. First, we have DEP, Data Execution Prevention. DEP marks regions of memory like the stack and heap as non-executable. This means even if you successfully inject your shellcode, it won't execute because the operating system refuses to run code from these memory regions. Second, the NX bit, the no execute bit, provides hardware-level enforcement of execution prevention. Modern processors support this at the CPU level, making it even more difficult to bypass. These protections were highly effective against traditional code injection. For a while, it seemed like we had solved the problem. But then attackers evolved their techniques, and that's where ROP comes in. So why would an attacker use ROP? What's the main objective? Let me highlight three key purposes. First, bypassing DEP and memory protection. This is the primary goal. Since ROP uses existing executable code rather than injected code, DEP doesn't apply. The code being executed is already marked as executable in the legitimate program memory. Second, evading signature detection. Traditional antivirus and intrusion detection systems look for known shellcode patterns. ROP chains don't contain traditional shellcode, so they're much harder to detect with signature-based methods. Third, enabling complex exploits. ROP is Turing-complete, meaning you can perform any computation. This allows attackers to build sophisticated exploit chains that can disable security features, escalate privileges, or establish persistence. The key innovation here, and this is crucial, instead of using a direct stack address pointing to injected code, we overwrite the instruction pointer with the address of our ROP chain. The ROP chain consists entirely of addresses pointing to legitimate code already in memory. Now let's dive into how ROP actually works. The process can be broken down into four fundamental steps. Step 1, identify gadgets, find useful code snippets in the target program. Step 2, chain gadgets, arrange these gadgets to perform desired operations. Step 3, control program flow, redirect execution through your gadget chain. Step 4, achieve arbitrary computation, execute your payload. Let's examine each step in detail. Step 1, identifying gadgets. What exactly are we looking for? We're searching for short instruction sequences that end in a RET instruction. These are our gadgets. The RET instruction is critical because it pops an address from the stack and jumps to it. This is how we chain gadgets together. We want gadgets that perform useful operations, data movement between registers and memory, arithmetic operations like addition or subtraction, and memory access operations for reading and writing. These gadgets are available throughout the target binary and any loaded libraries. On Windows, this includes system DLLs like kernel32.dll or ntdll.dll. On Linux, this includes lib and other shared libraries. A typical program might have tens of thousands of potential gadgets to work with. So how do we actually find these gadgets? We use specialized tools. Two popular tools are ROPR and ROP Gadget. Let me show you example commands. ROPR, f_target_program, search, popx, ret. This searches for a specific gadget pattern. ROP Gadget, binary, /target_program, only, MOV ret. This finds all gadgets containing MOV instructions followed by ret. These tools automatically scan the binary, disassemble the code, and identify all possible gadget sequences. They can search for specific patterns or catalog all available gadgets. Modern ROP tools can even automatically generate complete ROP chains for common operations. Some of you might be familiar with Mona.py for Windows exploit development, which is another excellent gadget finding tool that integrates with Immunity Debugger. Here you can see examples of actual gadgets you might find in a binary. Each gadget performs a simple operation followed by RET. Notice how each one is just a few instructions. We're not looking for complex functions, just tiny snippets that we can combine to build more complex functionality. The beauty of ROP is that by chaining many simple gadgets together, we can achieve complex computations. Step 2, chaining gadgets together. This is where the magic happens. The strategy relies on stack manipulation. Here's how it works. First, we place each gadget address on the stack. When a gadget executes and hits its RET instruction, it pops the next address from the stack and jumps there. Second, we position data and arguments between gadget addresses as needed. For example, if a gadget does popx, ret, we place the value we want loaded into EAX right after that gadget's address. Remember that the stack grows downward in memory, but our execution flows upward through the addresses. Gadgets execute in the sequence we've arranged them on the stack. This creates a chain reaction. Gadget executes, RET pops, next address jumps to next gadget, repeat. Let's compare normal execution with ROP execution. In a normal function call, you have call function, the function executes, then RET returns to the caller. Nice and linear. In ROP execution, it's a series of tiny jumps. Gadget 1 executes RET, gadget 2 executes RET, gadget 3 executes RET, and so on. Each gadget does one small operation and then immediately returns, causing the CPU to jump to the next gadget address on the stack. This unconventional execution flow is what makes ROP so powerful and so difficult to detect. Let me walk you through a concrete example. Our goal is simple. Write the value 0x41414141 to memory address 0x080490000. In normal assembly code, this is straightforward, just 3 instructions. First, move EAX 0x080490000, load the destination address to EAX register. Second, move EBX 0x41414141, load the value to EBX register. Third, MOV EAX EBX, perform the write of EBX value into destination address on EAX register. Simple, direct, efficient. But in ROP, we can't write these instructions. Instead, we need to find gadgets that can accomplish the same thing, like pop EAX, RET, to load the destination address. Then pop EBX, RET, to load the value. Also MOV, EAX, EBX, RET, to perform the write. Let's say we've identified these 3 gadgets at specific addresses in the binary. First, 0x080483887 contains pop EAX, RET. And second, 0x080485542 contains pop EBX, RET. Then third, 0x0804859 contains MOV, EAX, EBX, RET. Now we construct our stack layout. This is critical, watch carefully. At the top, we place 0x080483887, our first gadget address. Below that, 0x080490000, the destination address that will be popped into EAX. Next, 0x080485542, our second gadget address. Then, 0x41414141, the value that will be popped into EBX. Finally, 0x0804859, our third gadget address. Now let's trace the execution step by step. Step 1, buffer overflow redirects execution to 0x080483887. Step 2, CPU executes pop EAX. EAX now contains 0x080490000. Step 3, CPU executes RET, pops 0x080485542 from stack and jumps there. Step 4, CPU executes pop EBX. EBX now contains 0x41414141. Step 5, CPU executes RET, pops 0x0804859 from stack and jumps there. Step 6, CPU executes MOV, EAX, EBX, writes 0x41414141 to address 0x080490000. Step 7, CPU executes RET, either jumps to next gadget or crashes. And there you have it, we've accomplished a memory write using only existing code. Step 3 is about controlling the program's execution flow. The sequence works like this. First, a buffer overflow overwrites the return address, specifically the EIP register on x86, which is the instruction pointer that tells the CPU what to execute next. Second, the first gadget executes, performs its operation, then hits return. Third, return pops the next address from the stack and jumps to the next gadget. Fourth, this process repeats until the entire chain completes. This gives us complete control over the program's execution path, even though we're only using code that was already present in the program. It's like hijacking a train. You're not bringing your own locomotive, you're just switching the tracks to go where you want. Step 4. Achieving arbitrary computation. Once you have a working ROP chain, the final steps are: deploy the payload, trigger the vulnerability with your carefully crafted input. Monitor execution, watch how your ROP chain performs in the target environment. Debug chain failures. ROP chains can be fragile, you may need to troubleshoot gadget interactions. Refine for reliability and stealth, optimize your chain to work consistently and avoid detection. The goal is a reliable, repeatable exploit that achieves your objective, whether that's executing shellcode, escalating privileges, or establishing persistent access. Now let's look at real-world ROP implementation. One of the most common techniques is bypassing memory protection, specifically DEP or the NX bit. On Windows, we use the VirtualProtect function. On Linux, we use Mprotect. Both of these are legitimate operating system functions that can change the protection flags on memory pages. The brilliant attack strategy is this: use a ROP chain to call VirtualProtect or Mprotect, change a memory region from non-executable to executable, then jump to your shellcode in that now executable region. You're essentially asking the operating system, "Hey, could you please make this memory executable for me?" And because you're calling it through a ROP chain using legitimate code paths, DEP doesn't block it. Let's examine the VirtualProtect function in detail. This is a Windows API function, and you can find complete documentation on Microsoft's website. Let me explain each parameter: LP address, the starting address of the memory region you want to modify. This will be where your shellcode is located. DW size, the size of the memory region in bytes. Typically the size of your shellcode. FL new protect, the new protection flags. We typically use 0x40, which is page_execute_read-write, meaning the memory becomes readable, writable, and executable. LPFL old protect, a pointer where the function will store the old protection value. We need to provide a writable memory address here, even though we don't care about the old value. When this function succeeds, it returns true, and the specified memory region's protection has been changed. When VirtualProtect is called, Windows expects the stack to be organized in a specific way following the stack calling convention. From top to bottom, the stack should contain LPFL old protect, pointer to receive old protection. FL new protect, the new protection value, 0x40. DW size, size of region to protect. LP address, starting address. Return_address, where to go after VirtualProtect completes. This is the standard Windows calling convention. The function reads its parameters from the stack in this order, performs the operation, then returns to the return address. Our ROP chain needs to construct this exact stack layout before calling VirtualProtect. This is the challenge: we need to use gadgets to arrange the stack properly. Now, this slide shows a clever technique for calling VirtualProtect using the pushadd instruction. Pushadd is a single x86 instruction that pushes all 8 general-purpose registers onto the stack in a specific order: EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI. Here's the strategy we're going to use. We load our registers with specific values. EDI contains ROP and OP gadget for alignment. ESI contains pointer to VirtualProtect function. EBP contains return address, where to go after VirtualProtect. ESP contains LP address, our shellcode address. EBX contains DW size, size of shellcode. EDX contains FL new protect, 0x40 equals page underscore execute underscore read write. ECX contains LPFL old protect, pointer to writable memory. EAX contains shellcode address, to jump to later. Then we find a gadget that does pushED followed by a call or jump to the address in ESI. When pushED executes, it pushes all these registers onto the stack. Because of how pushED orders the pushes and how we've loaded the registers, the stack ends up arranged correctly for VirtualProtect to read its parameters. After pushED, the parameters are on the stack in the right order. ESI contains VirtualProtect's address. We call the function through ESI. VirtualProtect executes and makes our shellcode executable. Control returns to EBP, our return address. We jump to EAX, our now executable shellcode. This is a sophisticated technique that you'll commonly see in real-world exploits. This slide shows actual ROP gadgets that were generated by Mona.py, a popular tool for Windows exploit development that works with Immunity Debugger. Mona can automatically find gadgets needed for VirtualProtect chains and even suggest complete ROP chains. This is what real-world exploit development looks like. We use automated tools to find and chain gadgets. Notice how each gadget has a specific purpose in setting up the registers for our VirtualProtect call. Tools like Mona have made ROP exploitation more accessible, but also more prevalent. On Linux systems, we use a similar technique but with the Mprotect system call instead of VirtualProtect. Mprotect is the Linux equivalent. It changes memory protection on pages. The documentation is available in the Linux man pages. For the Mprotect function on 32-bit Linux, we need to set up these registers. EBX contains 0xFFFDD000, which is stack address ending with null byte. ECX contains 0x00021000, which is length of memory region. EDX contains 0x00000007, which is protection value. 7 equals RWX equals read, write, execute. EAX contains 0x00000007D, which is syscall number from Mprotect, 125 in decimal. After loading these registers, we execute int 0x80, which triggers the system call. Here's an important challenge. Notice all these values contain null bytes? On Linux x86, parameters are passed in registers, and if we're dealing with strcpy or similar vulnerability that stops at null bytes, we can't directly pass values like 0x00000007. This is where ROP really shines. We can use arithmetic gadgets to build these values without null bytes. For example, XOR a register with itself to get 0. Add small values incrementally to reach our target. Use bit manipulation to construct the values we need. This slide shows the ROP gadget template from Mprotect. You can see how we need to carefully construct each register value through a series of gadgets before triggering the system call. The process is similar to Windows but adapted for Linux system call conventions. Let's see how this works when we try to bypass memory protection on our local Linux machine. That brings us to the end of our presentation on return-oriented programming. To summarize what we've covered today, ROP is a powerful exploitation technique that bypasses modern memory protections by reusing existing code rather than injecting new code. We've seen how attackers identify gadgets, chain them together, control program flow, and achieve arbitrary computation. We've examined real-world implementations using VirtualProtect on Windows and Mprotect on Linux. From a defensive perspective, understanding ROP is crucial. Modern mitigations include Control Flow Integrity, CFI, Intel CET and ARM pointer authentication, ASLR to randomize gadget addresses, stack canaries and other compiler protections. The arms race continues. As defenders implement new protections, attackers develop new bypass techniques. Now, I'd be happy to take any questions you might have about ROP, exploitation techniques, or defensive measures. Thank you.